We will now finish our work on the Foucault pendulum that we started in the last video. So just to recapitulate what we did, here is our pendulum with a long L and a fairly small amplitude, so we can use a small angle approximation. This angle beta here is much smaller than 1. That combined with Newton's second law, taking into account the Coriolis force, and the centrifugal force is also of the Earth is also baked into this term here, the gravitational term. We arrived at these equations of motion in x and y for the Foucault pendulum, essentially a linearizing this equation with the beta much less than 1. And just to remind you, z, the vertical direction here, is up, and y is towards the north, x is towards the east. So we arrived now at these two coupled differential equations in x and y. And we're going to use the same trick we used a few times before to solve this. Essentially, we'll say that this is equation 1, this is equation 2. Let me move these to the side so that I have a little more space. And then I'm going to take, that actually is not a very good choice of names, equation 1 and equation 2. So I'm going to take equation 1 and I'm going to add in I times equation 2. And then I will get that x double dot plus iy minus 2 omega z y hat plus 2 omega z x hat times I plus omega naught squared times x plus iy equals 0. That's a little uneven. Okay. These two terms can be rewritten like this. And therefore, we can introduce a new variable, eta, which is equal to x plus iy, allowing us to find, when we solve the equation, x as the real part of eta and y as the imaginary part of eta. If we do that, well, that gives us just the differential equation, eta double dot plus 2i omega z eta dot plus omega naught eta equals to 0. So that is our new equation of motion that we can solve. Now, this looks very much like the equation for a damped oscillator. So just to remind you, if you have a damped oscillator, its equation looks like this. And it has the solution where omega 1 is the square root of omega naught squared minus beta squared if beta is less than omega naught. And we can take the solution and just carry it over here. The only thing that we get is that instead of beta, we have I times omega z. Right. So from this little box, we will get where omega 1 is the square root of omega naught squared plus capital omega squared. Right, and there's a plus sign there as opposed to a minus sign because we have this I here, which when squared gives you a minus 1. Now, omega squared, capital omega squared, is much smaller than omega naught. Omega naught is on the order of 1 over omega naught, the period, actually 2 pi over omega naught, is on the order of a few seconds, whereas the period corresponding to capital omega is 24 hours. So this is approximately equal to omega naught, and we'll just use that from now on. So this is the this is eta of t. That's the solution to this equation, a motion. But we're interested in the motion in x and y. We can just apply this to this equation, and we then get the final solution. So that is the solution to the motion of a Foucault pendulum. Now, what it looks like is that we have an oscillator with an oscillating phase or an oscillating amplitude, and that oscillating amplitude is 90 degrees out of phase in x and y. So if you were to plot what this approximately looks like, then initially, at time t equals 0, let's say, the way we've done things here, we've actually, I didn't say this, but we have taken delta to be 0 here. And if we do that, that means that initially we only have motion in x. Time t equals 0, the motion in y is 0. And the oscillator is moving back and forth along the x-axis. Then as time goes by, and the period here is omega z, as time goes by, after some time has passed, the oscillation has rotated so that it is now partially in the y direction, and this angle here is omega z times t. And this is exactly what we expect, right? This is the motion of a Foucault pendulum. The period of the period of the fast oscillation, of course, is omega naught, or 2 pi over omega naught. But there is also a period associated with the rotation of the Foucault pendulum's plane of swinging in the xy plane. Right, so that period is much slower, of course. So that period I'm going to call capital T. It's 2 pi over omega z. And omega z, I'll remind you, is omega times cosine of theta. Theta is the co-latitude, defined this way here. So that means that when theta is 90 degrees, then cosine of theta is 0. Right. So at the poles, at the equator, t becomes infinitely long. In other words, at the equator, the Foucault pendulum doesn't work at all. Whereas at the poles, as theta equals 0, then we have t equals 2 pi over omega, so that's 24 hours. So the time period, the period of oscillation, so the period of rotation of the Foucault pendulum is at least 24 hours, but it could be longer depending on what latitude you're on. And the closer to the equator you are, the longer it takes for the Foucault pendulum to make a full rotation.